Welcome to this class. It's about the problem in a combustion and fuels. In a closed combustion vessel, propane C3H8 and air with an equivalent ratio of 1.11 initially at 25 degrees centigrade burn to produce products consisting solely of carbon dioxide, carbon monoxide, water and atmospheric nitrogen. If the final temperature is above 1800 Kelvin, determine the heat rejected from the vessel. If the initial pressure is 1 bar, estimate the final pressure. Lower calorific value of propane minus delta H naught is 2039840 kilojoule per kilomole of fuel at 25 degrees centigrade. As neither oxygen nor hydrogen is present in the combustion products, this implies that dissociation should be neglected. First, we have to write given closed combustion fuel is propane C3H8. Then with an equivalent ratio, that is 5 is equal to 1 at temperature is equal to 25 degrees centigrade. The products consisting solely of carbon dioxide, carbon monoxide, water and atmospheric. If the final temperature is 1800 Kelvin, determine the heat rejected from the vessel is equal to 1800. If the initial pressure is 1 bar, estimate the final pressure. Initial pressure is 1 bar, estimate the final pressure. Minus H naught, that is lower calorific value of propane, 2039840 kilojoule per kilomole of fuel. No dissociation. Find 1. If the final temperature is equal to 1800 Kelvin, heat rejected from the vessel. Here, if the initial temperature P1 is equal to 1 bar, find the final pressure. In a closed combustion vessel, propane C3H8 they given. They are asking what is the heat rejected from the vessel, what is the final pressure. First we have to write the combustion equation. The fuel is C3H8 propane. Then combined with air to produce us CO2, H2O and N2 for a complete combustion, that is for complete combustion. 1 mole of propane reacted with Y mole of air produces A mole of CO2, B mole of H2O, C mole of N2. Now we have to find out what is the amount of air required for the complete combustion. There is a shortcut way. If a fuel is CaHbNCOD, it's a CHNO system. For complete combustion, stoichiometric air required, that is in this case we given it as Y, is equal to A plus B by 4 minus D by 2. So here A is equal to 3, then B is equal to 8 by 4 minus 0. We can get the air fuel ratio is 5. Now the equivalent ratio is given. 5 is equal to 1.11. The definition of equivalent ratio, stoichiometric air fuel ratio over the actual air fuel ratio. So that we can find out what is the actual air fuel ratio is equal to 5 is the stoichiometric air fuel ratio, then equivalent ratio is 1.11. We can get 4.5 is the. Now the actual combustion equation becomes 1 mole of propane combined with 4.5 mole of air to produce some amount of CO2 and some amount of CO, 4 mole of H2O, 3.76 multiplied by 4.5, 16.92. We don't know what is exact amount of CO and CO2. However, the summation of CO plus CO2 should be 3. Assume that the amount of CO is equal to X, the amount of CO2 will be 3 minus X. To find out this X value, make an oxygen balance. In the left hand side, it will give 4.5 multiplied by 2, and in the right hand side 3 minus X multiplied by 2 plus X plus 4. Upon simplification, we get X equal to 1. Now the exact actual combustion equation becomes 1 mole of propane, then 4.5 mole of air to produce 2 mole of CO2, 1 mole of CO, 4 mole of H2O, 16.92 mole of N2. Given that lower calorific value is equal to minus delta H naught is equal to 2039840 kilojoule per kilomole of fuel. This calorific value is the not for lower calorific value is the reaction without CO. However, in our exercise, they given that CO is present in the products. So that we have to consider this one. So for this reaction, delta H naught is equal to delta H naught without CO minus number of kilomoles of CO multiplied by delta H naught with CO. This one is given. We have to find out what is delta H naught with CO. For finding out this CO, we have to go for a reaction, that is CO plus of O2. It will be producing CO2. So the CO of delta H naught of CO is equal to H of CO2 minus H of CO minus half into H of O2. This is H is the absolute enthalpy. At 298.15, that is 25 degrees centigrade, H of CO2 is equal to 393.512 minus of H of CO minus 110.525 minus half into O2 is 0. So upon simplification, we found that this one is equal to minus 282.987 megajoule per kilomole. We can multiply this 1000, we can get minus 282.987 kilojoule of fuel, kilojoule per kilomole of fuel. With CO minus 282.987, when you are substituting in this equation, minus of minus 282.987, then without CO minus 2039840, we can get plus 1756853 kilojoule per kilomole of fuel. So we found that this lower calorific value or enthalpy of reaction, enthalpy of this reaction, we found that plus 1756853 kilojoule per kilomole of fuel. However, they given the heat of reaction is carried out by constant volume, so that we have to convert this calorific value at constant pressure. Calorific value at constant volume is equal to calorific value at constant pressure minus number of reactant, number of product difference multiplied by R naught into T. So this calorific value at constant volume is equal to 1756853 minus number of product and number of reactant. We derived a calorific value at constant pressure of this reaction. Then we need to find out what is the number of product and what is the number of reactant. So from that equation, number of reactant is equal to 1 mole of fuel plus 4.5, 1 mole of oxygen, 3.76 mole of nitrogen, 22.42 kilomoles. Then number of product is equal to 2 mole of carbon dioxide plus 1 mole of carbon monoxide, 4 mole of water plus 16.92 mole of nitrogen. It will give 23.92 mole of the product. So we can simplify this equation by calorific value at constant volume is equal to 1756853 minus of number of mole of reactant is equal to 22.42 minus 23.92 multiplied by R naught 8.314 multiplied by temperature 298. We found that this calorific value at constant volume is equal to 176,0569.36 kilojoule per kilomole of fuel. Now we have to find out what is the heat of the reaction. That is calorific value at constant volume is equal to change in internal energy of 1800 minus change in internal energy of 298 minus Q. Internal energy at 1800 minus internal energy at 298 of CO2 plus internal energy at 1800 minus internal energy at 298 of CO plus internal energy 1800 minus internal energy 298 of H2O plus internal energy at 1800 minus internal energy 298 of N2. How many moles of this? 2 moles of CO2, 1 mole of CO, 4 mole of H2O, 16.92 mole of N2. From the internal energy table, at 1800 CO2 minus 329.117. So delta U of CO2 is equal to minus 329.117 minus at 298 minus 395.991. Delta U of CO is equal to minus 76.003 minus 76.003 minus 113.004 delta U of H2O is equal to minus 194.178 minus 194.178 minus of minus 244.303 minus 244.303. Then N2 33.983 delta U of N2 33.983 plus 33.983 minus 2.480 minus 2.480. This CO2 multiplied by mole of CO2 2, CO multiplied by mole of CO 1, then H2O multiplied by mole of H2O 4, then N2 multiplied by 16.92, we can get delta U of CO2 133.748, for CO 37.004, then H2O 200.5, then N2 616.953, then summation of this one, it will give 988.205 megajoule per kilomole of fuel. We need a kilojoule per kilomole, so 988.205 kilojoule per kilomole of fuel. Calorific value at constant volume is equal to delta U of this reaction, delta U of reaction minus Q. Calorific value at constant volume is equal to 1760569.36 is equal to delta U is equal to 988.205 minus Q. Then Q is equal to minus 772,364 kilojoule per kilomole. Then that is equal to minus 772.364 megajoule per kilomole of fuel. This negative sign implies that heat flow from the vessel. Now come to the second question. If initial pressure is 1 bar, find the final pressure. We know that the relation, ideal gas relation, PV is equal to N R naught T, and for the reactant we can write P of the reactant, volume of the reactant is equal to N of reactant R naught multiplied by T of reactant. So we can find out what is volume of the reactant is equal to N of reactant, R of reactant and T of reactant divided by P of reactant. That is equal to N of reactant is equal to 22.42. Then R naught you keep it as R naught, and then T of reactant 298. Then pressure is equal to 1 bar. Volume of the reactant. Similarly, when you are writing for the volume of the product is equal to moles of product R naught multiplied by T of the product over the pressure of the product. So, in a closed combustion vessel, volume of the reactant is equal to volume of the product. We can equating these two, we can find out 22.4 tau into R naught multiplied by 298 over 1 bar is equal to number of product 23.92 R naught multiplied by 1800 over pressure of the product. So the pressure of the product is equal to 6.44 bar. So this is the final pressure. So the first step we have to write the chemical reaction for complete combustion. Chemical reaction for complete combustion. Second, with an equivalent ratio given, we have to write the actual combustion reaction. And third, we have to write what they given. They given calorific value delta H. It means that calorific value at constant pressure. So we have to convert this calorific value at delta H, calorific value at constant pressure without CO. So we have to find out calorific value at constant pressure with CO. Then the calorific value at constant value by the relation, then equal this calorific value at constant reaction is equal to enthalpy delta U minus Q. This Q is the heat rejected from the vessel. And the seventh step is P1 is given, T1 is given, similarly T2 is given, And we know that number of moles of the product and the number of moles of the reactant, number of moles of the product, then we can easily find out volume of the reactant is equal to volume of the product. We can easily find out the pressure of the product, that is the final pressure.
Subscribe to our channel, like if you're satisfied, and share because it may be useful to someone.